Welcome to the next segment of High School Geometry with Netz and Weichel. This is Mrs. Netz.
And this is Mrs. Weichel.
Today we are going to be talking about 1.3 logic notes. Our learning target for today is that we will be able to use logic to recognize when a proof is flawed and should not be believed. Why do we need to understand logic and proofs? Because thinking logically is a life skill that can either save us from bothering with doing a problem or allow us to work in confidence knowing that there actually is an answer. You will know that you have mastered this when you can use logic to check your reasoning on different geometric ideas.
So let's go ahead and get started. First of all, what is logic? Logic is a science that helps you make decisions based on facts or circumstances pertaining to an event. So you can't just go in it willy-nilly. You actually have to have some facts to help you come up with a decision, come at it with a game plan, ready to think through something with reason. You have to have reasons for why you're doing what you're doing.
Okay, so let's talk about the three different types of logic. Our first type of logic that we are going to talk about is intuitive. And think of, you can write on the side or underneath in the box that says type. Intuitive is much like the word intuition. Okay, the definition is you reach a conclusion based on your feelings or your intuition. It's almost like you're going with your gut.
So what I see a lot of times is like lottery tickets. If you play the lottery and you go with your gut feeling on numbers that you're going to play, or you always play the same numbers because they're your lucky numbers, that's your intuition telling you to do that.
Okay, so now our second type of logic is what we call inductive. So inductive is a process of reasoning that something is true because all other cases are true. And we're going to give you some ideas to help you connect inductive to the different types of inductive reasoning when we get to the bottom of the notes page.
And then the last that you'll use most often in this class is deductive reasoning, which is a process of reasoning where conclusions can be made from known facts. So it's actually the exact opposite of inductive reasoning in that we have a triangle for you at the bottom of the page that you can start to fill out. Inductive reasoning is when something was tested on something specific and then a general thesis or a general idea of something was made from it. Whereas deductive is a very general statement about all things, and then you can specifically apply it to your specific case that you're working on. Inductive, again, is if you take one person and you assume all of their friends are going to be similar to that. So
like you've heard all the time that if I'm smart, then all my friends must be super smart too. Or if I love math, all my friends must love math too.
that would be inductive reasoning. Whereas deductive is the exact opposite of that, where you take a very general statement and apply it to something specific.
So you see a bunch of people that you know enjoy math, and then you go, oh, well, they all must absolutely enjoy math because they're all sitting in a math classroom giggling, laughing, having fun. That doesn't mean everybody in the room actually enjoys math.
Mathematically speaking, for deductive reasoning, what we learned about in 1.2, if you see a straight angle, you know all straight angles equal 180 degrees. So if I give you straight angle GOT, you would be able to make specifically the statement that angle GOT must equal 180. So a very specific statement of straight angles equal 180 to specifically, well, GOT is a straight angle, so GOT must be 180 degrees.
One that you all are, a couple of examples that you're probably more accustomed to hearing, they're generalizations or stereotypes. So for example, deductive, you'll hear people say, well, oh, all jocks are dumb. So if you're a jock, that must mean you're dumb too. Which that is your deductive reasoning. You assume something to be true about the group. So because it's true about the group, it must be true about
every single person
in the group. And then your inductive would be like when you say that Oh, well, I know she's a jock. So all her friends must be jocks too.
Right. So again, based on what we're going to be doing in this class, you'll more often be using deductive reasoning because we'll be teaching you very general statements about geometric ideas and topics, and then you're going to apply them to specific problems that you are working on in class.
Okay, so let's go on and talk about some different type of statements with logic. So our first one that we're going to talk about is a conditional statement, or think about it like conditions. And the easiest way to help you all remember this is your parents give you conditional statements, like I'm going to say daily.
I would assume daily.
If you do the dishes, then you can go out.
Right.
If you clean your room, then you can have dinner.
Oh, I hope that's not it. Starving the children.
Well, then you can have,
Dessert?
sure, whatever. Okay, so anytime you hear this if then, that is a conditional statement. If you do this, then that will happen.
So many times you'll see this abbreviated. I believe you'll see it in Khan Academy when you're working on there. You'll see the letters P and Q be used. So if P is true, then Q will also be true. So I have that example written here. You have a line. You can go ahead and write that. You will also see it with the arrow notation, P arrow Q. That is just a mathematical abbreviation of if P, then Q. We looked up why P and Q are used. I thought this was kind of interesting.
I did too.
The letter P, they started using this when typically talking about conditional statements because it stands for P for proposition. So you're proposing something, an idea about something. And
the reason they use the letter Q is kind of, I hope you're ready for this. You may want to write it down. This is kind of very, yeah, this is mind-blowing why they use Q.
It's the next letter in the alphabet after P.
What?
Amazing. Mathematicians are amazing.
So the use of P and Q really only has to do with
the alphabet.
And the letter P is
for proposition.
Proposition.
It's crazy.
Great.
So a conditional statement is literally taking information and writing it in if-then form. So we have an example. You have space underneath the line that we would like you to write this in. Talking about something that I think would be very easily shown as a true statement. If you know it's a Saturday, then you know it's the weekend. So we could write that as, if it is Saturday, then it is the weekend. So go ahead and fill that in just as an example specific to this problem. Again, you have a space for you to fill in the if P, then Q, or with the arrow notation. And then right below that, you can go ahead and write, if it is Saturday, then it must be the weekend, or then it is the weekend. Another important statement of logic is the converse statement. And the converse statement is when you simply take the conditional that you're given and you're going to flip the order. You're going to take the hypothesis and the conclusion and switch them. So instead of saying if P, then Q, it's going to now state if Q, then P, or the arrow notation would be Q and then arrow P. So in the conditional statement you were given, we were talking about the day of the week of Saturday, and then the fact that that is a weekend. So the hypothesis is that it's Saturday, and the conclusion is that it is a weekend. So why don't you go ahead and pause the video and write the converse statement of that conditional statement. Okay, so hopefully you just, again, flipped the order. So instead of talking about the fact that it's a Saturday, you're going to first talk about the fact that it's the weekend. And if it's the weekend, then it must be Saturday would be the converse statement. And once you have these two statements, you have to start thinking about whether these statements are true or false. In this case, would you say our conditional statement, what I have up here at the top in the black box, is that a true statement? That if it's Saturday, it's the weekend?
That doesn't make much sense, because what about Sunday?
That's the converse statement. So conditional statement would be true, because if it's Saturday, it is included in the weekend. But then our converse statement would be the false statement because of what Miss Nett said. If it's the weekend, well, it doesn't automatically make it Saturday, because it could be Sunday, which leads us into our two vocabulary words next.
So just know that your converse could be true or could be false.
I would say 90% of the time we will work with a true conditional statement. And then the converse, true or false, is where you're going to decide what you'll do next, whether you're going to write something called a biconditional statement or a counterexample.
So a biconditional statement is if both the conditional and the converse are both true. So think of it like this: biconditional. You know it's conditional because we are a conditional statement of what we started with. Bi meaning to. So biconditional statement means that both the conditional and the converse are true, and our statement is then written as if and only if form.
So if P then Q is true, and if Q then P is true, you can combine them and make one sentence saying P if and only if Q. We would not be able to write that with our example because
they're both not true.
They're both not true. It doesn't work both ways.
What messed us up was if it's the weekend, then it's Saturday. But we know darn well Sunday's the weekend. So we cannot write a biconditional for that statement.
For our example, Sunday is actually our next vocabulary word. Sunday is a counterexample to that converse statement because you're proving it false. So a counterexample is a specific example that proves it false. This will be on the test. If we gave you the statement, if it is Saturday, then it is the weekend, and if it's the weekend, then it's Saturday, and we ask for a counterexample, all you would simply say, Sunday. Sunday is a counterexample to that statement because you're proving it false.
So, for example, if I were to say, I was born in Arizona, then I was born in Phoenix.
That would be false because a counterexample would be Sun City West.
Or Peoria, or
Flagstaff,
Gilbert,
Tucson.
or so many other cities. So if I tell you something and you sit there and you go, but wait a minute, what about
if this were true?
What about this?
What you're thinking of are counterexamples.
Counterexample just means you're countering me. I've said something, you're coming back and going, maybe not so much, and here's why.
What if I said, if two lines are in the same plane and never intersect, then they must be parallel?
I would say that...
Is there any counterexample that you could think of for that, or would we be able to write a biconditional statement?
I would then say that my counterexample would be skew lines.
Skew lines are not in the same plane.
Oh, you are right. You said same plane?
I think so. I thought I did.
Then the only type of parallel lines in the same plane would be parallel lines.
So then you would be able, that would be an example of being able to write biconditional statements. So you could say lines in the same plane that never intersect, if and only if they are parallel. Or parallel lines are parallel if and only if they're in the same plane and never intersect.
Awesome. Okay, now let's talk about our law of detachment and our law of syllogism. Okay, the law of detachment allows you to detach the hypothesis from the conclusion. So basically what we're saying, if both P and Q...
So if P then Q is true, and part P of a statement is true, then you're able to basically detach P and Q. You'll be given a statement about P, so your answer, your conclusion would be something specific about Q. This is deductive reasoning. If you have a general conditional statement, if then form, then something specific about the hypothesis, about the P part, you will then say something specific about that situation for the conclusion or Q.
Okay, and then our law of syllogism allows us to squeeze two conditional statements together. So you could say, for example, if P then Q, and if Q then R, then...
Basically, they're both connected by Q. If P then Q then R, you can basically cut out the middleman, take Q out, P then R must be true as well. So this very frequently you'll actually hear it called the chain rule.
So we're like saying if A equals B and B equals C, then A has to equal C. Because if they are both equal to this middle letter, middle link, because this middle letter is linking the whole thing together. So hence the chain rule.
There you go.
All right. So now let's go on to more
Our last
vocabulary.
page. Lots and lots of vocabulary. You'll be able to do a big part of your vocabulary section today.
Yes. All right, so let's talk about first, we're going to talk about some properties of equality. And most of these you all know. So you have your addition property of equality. That's if A equals B, then A plus C equals B plus C.
So in simple terms, it's when you add to both sides of the equal sign. For subtraction property of equality, if A and B are equal, then A minus C must be the same as B minus C. So again, similar to the name, it's when you subtract on both sides of the equal sign. The multiplication property of equality, if A is equal to B, then A times C must be the same as B times C. Then lastly, the division property of equality is probably what you guessed. It's when you divide both sides by C. There is a little bit extra here because you cannot divide by 0. The statement would be if A is equal to B and C doesn't equal 0, then A divided by C would equal B divided by C.
So you can think of all of these as your properties of equality. These are all your
When you're
tools,
solving equations.
all your tools you used when you went to go solve equations. Okay, so next we're going to get into a couple of other properties. We have our substitution property we're going to start with.
If A is equal to B, then B can be plugged in for A in any expression. So you guys used substitution in Algebra 1 when you were doing system of equations.
That you used substitution property in probably first, second grade. If the blue box equals 3, what is a blue box plus 1? Well,
So you would substitute 3 in.
you put 3 in where the blue box is, and it's 4. That's the substitution property, and that's how long you've been using that property for and didn't even know the name of it.
There you go. Transitive property, the way that we explained it a little bit ago is actually something we learned already. It's just a new name, and it's dealing specifically when you're talking mathematically. Transitive property is going to be very similar to your chain rule. If you look back at what we said the chain rule was, chain rule.
It's like you have this middle piece that is linking the whole thing together.
If A is equal to B and B is equal to C, then A must equal C. So we're talking in terms of equations here. You can also have congruency statements. So those could be if A is congruent to B and B is congruent to C, then A must be congruent to C. Reflexive property. I like to give this example because it helps students remember it, but please don't spell it wrong. Reflexive property is when something is shared or something is equal to itself. Much like when you look in the mirror and see your reflection, you're looking at yourself. So this is not the reflective property, though. It's with an X. It's reflexive
And
property.
it's also not the reflection property.
Not the reflection property. So again, I use that as an example just to help you understand it, but make sure you are spelling these correctly. It is when something is equal to itself. So in this case, when A is equal to A. And then lastly, symmetric property. Symmetry, I'm sure you learned about in your art class, probably in elementary school. I can remember doing a project where half of my face was printed, and I had to draw the other half of my face. That is the symmetric property, basically.
So think of it like this for my algebra thinkers. If x equals 5, then 5 must equal x.
So kind of like a butterfly. I also picture a butterfly here. I like butterflies.
Yeah.
So if A is equal to B, then B is equal to A. You basically flip the equation around and you have your symmetric property. So I believe that is the conclusion of our logic notes. On the back of our notes, we have a nifty little logic puzzle for you.
Now, on that logic puzzle, please notice that on the second paragraph, you can cross off everything except that first sentence. It talks about clicking on some links and all that good stuff, and those links are no longer there. So go ahead and make an attempt at this logic puzzle. I would encourage you to involve other people, other adults, other students, and I would love to see how logically you can think.
Talk to your parents about this.
Can you figure it out?
There's zero geometry technically on here. Like, this is straight logic.
Now, I will give you a small piece or two small pieces of advice. Once, use a pencil. Oh
Definitely
my gosh.
do a pencil.
You'll be erasing a little bit every time you're like, wait, but that won't work. And then also, I would use X's for things that you know to be absolutely not even possible.
So go ahead and try that. Hopefully today's lesson was somewhat of an easier lesson for you, just a lot of vocabulary. So it's really, really important that you're learning these vocabulary terms to make the actual process of utilizing them to be a little bit easier for you. All right, so if you struggled at all, as always, please message us on Remind or email us, or if we're not your teacher, please contact your teacher.
Absolutely.
Any one of us can help you guys. So that's about it.
That is. So now, Mrs. Weichel,
What, Miss Nets?
what do you get when Mrs. Weichel and Mrs. Nets look for jokes on logic?
What?
Nothing. We couldn't find anything.
We've been looking for a while, and yeah.
Yeah.
If you can find a funny joke about logic,
please send it to us.
send it to us via Remind.
All right. So good luck on your logic puzzle. Good luck on your homework. May it all be very logical, and we'll see you in our next lesson.
Thanks.
George.